Okay, welcome all. We will officially get started. I have one lecture left. I have to lecture this because it's on the final exam. And in order for me to properly cover all of the material, I definitely have to go through this. And then after I get done with this, we will do the final exam review, which I know you guys are all here for. So I'll try to make this as painless as possible and cover the main points. And I'll also cover some of the architectural design points as well. Make sure to sign the roster that's going around so you can get attendance for being here. And where's my TAs? Nothing about where is everybody today anyway? I was expecting a good turnout because you guys all want to know about final exam. So I guess you really don't want to know about the final exam. Or everyone's waiting because they know I'm going to blab for about an hour before I get into it. So they're gonna come in about an hour is what they're going to do. I have a strange feeling. Anyway. But you guys are lucky. You actually get more content. You get more information. So this last lecture is lecture number 11, and this is where it stops, actually. After this lecture, the content, and I'll go through it specifically in a few minutes. But this one is the extension off of the architectural design, and it gets into the concept of software design and reuse. And it's not necessarily object-oriented. It talks about the reuse component. And it also talks about components, which is one of the themes that's covered on the final exam, which is the reason why I have to cover this, actually. It would not do you justice to leave this out. So what are we looking at? Explaining the benefits of software reuse and some of the reuse problems that exist, because in modern day software engineering, reuse is very important in terms of the concept of making something efficient, minimizing a lot of the workload, making it reliable, dependable, making it easier and compatible. So I'll talk about some of those issues and describing the different types of reuse components and processes as well. And then looking at and introducing some of the application frameworks and some of the families. So introducing application families as a route to reuse, which is really the important part of this lecture as well, another component that's on the final exam that we need to look at. So I'll kind of go through and I'll highlight what you need to know. But at the same time, it's a nice overview of the concept in terms of what the modern trend is. The lecture actually goes through the concept of component-based development. And as we've seen with our architectural design, lectures numbers 12, 13, 14, or whatever are into specific domain architectures. So if you remember at the end of my architectural design lecture 10, I believe it was, I talked about domain architectures, client-server models, peer-to-peer models. This actually kind of extends the concept as well and fills in some of the gaps in terms of the component level design, because essentially with an architectural design you're doing component-based development. You're developing component after component. You're putting the components together and you have the sum or this application that's created from it. And then we have these application families that kind of go along with it, and then it also brings up the concept of design patterns, which is something I also needed to cover in software engineering too, to give you, the fullest background of all of the information that pertains to this. So let's get into the concept of reuse momentarily. What we're looking at is being able to use existing components over and over again. If we model the software in terms of its components, then we can facilitate a system that's going to work with reuse. And we can move the focus from original development to recognizing and achieving better software to more quickly lower cost development, which is kind of the route that object orientation takes, especially with inheritance and the class hierarchy. We reuse existing classes, but this is really above and beyond that concept. Software reuse is more along the lines of working with reusable components and building the software design on a component-based theory or component-based process so that we can actually facilitate this. So systematic reuse is one of the terms that comes up. And so as it applies towards architecture and applies towards software engineering, what we're looking at is the application system reuse, where we can take a full application system and modify it. So it's the whole application that's reused. And this is where we get those COTS. And you need to actually know the word COTS. It's off-the-shelf software, where it's a pre-built program that we're reusing and we're customizing it. And I talked a little bit about that in the Software Engineering 1 course. And the concept was that it was easy because it was already in existence, and we just modified it to meet our needs in terms of the application, which kind of works, but in the long run, it actually costs you more money and takes more time. Because every time there's an upgrade to that COTS package, you have to do an upgrade, or you have to do a change all over again for your customization. So customizing something that already exists, although it's a kind of a part of reuse, not desirable. It's better to build a software package from scratch using components, design the components for reuse. And so then that brings into the architectural framework. And then also the platform and the framework for which the application is being built. Because you really have to think about that ahead of time. Does people want to come in? I don't know. They're waiting for the final exam review. So anyway. All right. So we have component reuse, and then we have function reuse as a concept. So knowing the different types of reuse is important in terms of the final. But the component reuse, looking at the application of subsystems into smaller objects that are reusable by component. And by definition, the function reuse takes it a little smaller. So you can actually kind of measure this with levels of abstraction. And take the high-end application, component, function, module, kind of procedures, and kind of just separate it out into different levels. In terms of the practice, we have application system reuse. So we have widely acceptable practices for modifying off-the-shelf type software applications, component reuse and function reuse. Wait a minute. Is that the same slide? Nah, it's pointing out practice-related information. So similar bullet points. In terms of the component, the key is to widespread reuse through component-based software engineering. And you can actually take a course in component-based software engineering. It's generally like a software engineering 3 or special topics class. Oh yeah, and a side note, for those of you who haven't taken software engineering 1, I know there's some people in here who have taken the 2 but haven't taken the 1. We're actually offering the 1 in the summertime. And yes, you can take 1 after you take 2. They're entirely 2 different courses. In software engineering 2, this is a slight tangent, we covered a bunch of, and we'll see it when the final exam, when I start looking at those different topics, wide range of software development application level and practice level type of information and concepts. In software engineering 1, it's more of the basics. It's more of the building from a software development lifecycle. It's more of testing procedures, how to actually do some of the things that we talked a little bit higher level on in terms of this class. But there are 2 separate classes with 2 separate focuses. So you're not going to be bored in 1. It's a totally different environment. But I know some of you have actually taken the 1. But I know some people didn't. Okay, so let's move on to the benefits of reuse. Increased reliability. And if you can think about the concept, taking it a little step further, when we test something, when we do regression testing, every time we've worked it. We've got that component pretty reliable to a certain point. If we're working with something that's already been through the ringer, then we can actually kind of have more confidence in that when we reuse it. And if we have more confidence, it's going to, the entire application itself, if it's built from reusable components, will theoretically have a higher reliability to it, just through, osmosis, I guess, or just through the concept of reusing the component. And then also you're reducing risk, because if you remember everything I said about reliability, and this is kind of a summary as well in terms of that concept. What we're doing with reliability, we're reducing the risk of a problem occurring. So if we reduce the risk, it gives us higher reliability. May also lead to that concept of dependability that I talked about in this course as well. And then we have the effective use of specialists. So we can reuse components instead of people. And so if we had a specialized algorithm created to do encryption or something, or if we had this package or this API created, we reuse it. In fact, that's the same concept, similar concept with application programming interfaces. Not only do they provide a wrapper onto lower level functionality and make it easier for you to implement the API in terms of your application, it's reusable. You create the application programming interface, you make it for this language, for that language, and it becomes a component of the software that you could upgrade, swap in, swap out, and as long as the interfaces stay the same, and it's an object-oriented kind of environment usually, and the interfaces do stay the same, then you're reusing the functionality, essentially. All right, so standard compliance as well, embedded standards for reusable components. If it's done in a reusable fashion, we're paying more attention to the interfaces to it. We're also paying more attention to the functionality, to the standardization of it. And then accelerated development, so you avoid original development, speed up the production a bit, and all in all, the benefits look pretty good, don't they? In fact, if you were to ask any of the software engineers out there, what's the best thing about reuse? And that's why everybody is like object-oriented analysis, object-oriented design facilitates reuse. Well, there's also requirements that have to be followed for this perfect world to kind of exist. And I tell you, it's not really a perfect world, because just because the component was already created doesn't really guarantee that the component is appropriate for its particular reuse or its particular application or new application. So requirements in terms of the design must be possible to find appropriate reusable components. So usually algorithms, especially if they are self-contained, like you send it in, you send input in, it does something, and then the component outputs something that's reusable in terms of the formats. So designing the component as a self-contained unit, which leads into and this is the reason why I have to mention this lecture actually, is it builds into the concept of the architectural design. Do you have a module or an object that's doing this functionality? Do you have one that's doing this functionality? Are they self-identifiable? Is it a print object that's printing? Or is the print object also doing scanning? Or is it also doing something else or providing something else that it probably shouldn't be providing? So the identity of the component, the appropriate reuse, whether it's being reused appropriately, is also a consideration, and must be documented as well. Which means if you have, in fact, this is the main part of what ends up happening. You have a situation where you've purposely designed the application for reuse, and you've got all of these components that you're going to take and assemble again and use, but nobody knows about them. It's kind of like how businesses install software on their network all the time, and the package is sitting out there, but nobody knows it does something, or nobody knows. In fact, half you probably don't know all the features of the EMS, as an example. Yet they're there. So the documentation, getting the word out, spreading the word on the feature. But in a software development environment, you got to rely upon knowledge of the people who wrote the component, as well as the documentation that goes along with it. And nobody likes to document anything. You all know that. So, all right.
The component itself is being built from the document, right?
The component itself should be. Well, that's the interesting concept. You could do the documentation first, and then build the component second. Or if you're reusing a component that somebody else wrote and there wasn't any documentation for it, you can later provide the documentation. And the more documentation you provide for it, the longer lived the component. What you don't want is a bunch of stuff on the network, a bunch of stuff in a repository that you don't know how to use. In fact, actually, that's kind of like one of the reasons why people don't take advantage of all the features of an API, because they have no idea what the features are. They don't even know half the functionality that's there. And then they realize, oh, that does this too? Why did we rewrite it? It's kind of like how people used to use applications before they got computer savvy. They bought Microsoft Office, and then they bought an Excel program extra. It's like, well, it's included in Office. It's like the total waste. But companies actually do that a lot because they don't even know what they have in terms of a repository of features. So, being confident that the component will also be reliable and will behave as specified is also kind of one of the issues as well in terms of the design. Let's talk about some of the problems of reuse, because this is the flip side. This is everything that could go wrong with it. We have increased maintenance cost. Because now maybe we have different platforms that some of the stuff was written on. Maybe we have different programming styles, different languages. Maybe we have different components that are acting as middleware that are putting everything together. Long story short, maintenance costs are usually higher in terms of keeping that up. Plus, you also have to be very careful if you're reusing a component that's interfacing with another program. You can't change the public interface to it, and you might actually be restricted in terms of some of the functionality. You can't just add anything to it arbitrarily and expect, the component to work. Another problem might be a lack of tool support that might exist. And with the tool support, it might be nothing more than having the right compiler, having the right environments, having the right platform, so that you can actually, make the modifications needed, maintain it in terms of its integration with the program. Not invented here syndrome. I always like that one, where it's, oh, we didn't make it, somebody else wrote it. Oh, well then that's their fault. And so what you do is, usually the engineers will kind of, well, let's just call the guy up or send him an email message. Hey, we had a problem with your program, blah, blah, blah. Yeah, it's like, what do they call that, the taillight guarantee? You guys heard the taillight warranty? I don't think it applies to software. It usually applies to selling cars. The warranty is as good as far as you can see their taillights. When you can't see their taillights anymore, they're gone. There's no more warranty. There's no more support on that product. It's taillight guarantee. It's an old joke. You guys didn't get it. I don't know. All right. You're not in the funny mood. You're all in the serious mood today. You're all like, get to that final exam review. No. Can't. Not yet. All right. So maintaining a component library. Making sure or actually being able to maintain a component library is possibly an issue. Finding and adapting reusable components. If you're not thinking about it, if you have a spread out team that is all over the place, you might not necessarily know that somebody wrote the algorithm to do the encryption, or that we already have this module created. So it might be hard to find, might be hard to actually adapt depending upon the application environment. Now, in a perfect world, if everything were written in the same language on the same computer system, and maybe just the same network would work, but the same group of people, and you all worked in the same office together, and you were sharing all that information, that would actually facilitate some really good reuse. But that's not really how the world works anymore, so it doesn't happen. We also have another kind of interesting phenomena that occurs, and the reason why this is in here is to kind of point out how architectural design and software development actually works alongside with the development. Because you can have what's called a generator. So generator-based reuse, you have a program generator that's involved in the reuse, and you have standard patterns and standard algorithms that are created. This is kind of like using open source or existing libraries and features where it's standardized, and what you're doing is you're embedding the generator, the parameters, and everything into the program, and it's automatically generating the code. So in some of the, there's a lot of chatter, in some of the UML designs in the beginning, and in some of the, like the rational rows tools, and some of the object-oriented analysis and design tool sets, it actually had code generation. And what it would do is you'd take and create an object diagram, an architectural diagram of your system. You'd click a button, and it would give you the class templates. And it didn't fill in all the method bodies for you or anything like that, but it gave you, all the states, the behaviors, and everything. And it generated source code for you. And you could do that in terms of, and it reused patterns. So if you had a model view control, and I'll talk about that in a few minutes, it will take the model and generate the code to meet that specification and standardize it, which really helped facilitate the reuse concept. So you could reuse generator-based reuse is also possible with domain abstractions and with mapping the executable code. So in terms of the domain-specific language, it's used to compose the control in terms of the abstraction, so you can use it essentially on a domain-specific environment to give you the architectural design that's needed for that environment. As an example, you had a code generator that knew it was a client-server environment. When you clicked the button to generate the code, it would have all of the interfaces set up and the entire architectural design of the code set up, so you had a client, a server, and you had the communication channel already established, and you had all of the components necessary, even the ones you didn't think about, which is why in terms of reuse, you're reusing a design pattern, and it's basically being done through a code generator. And it's a form of reuse in development. And it's not what I'd call automated, because you always have to edit it. and it's not what I'd call foolproof either, and it doesn't replace programming skill. You can't rely upon generators. And it's not in a slide set, but those are some of the negatives that are associated. So people relied too much on the generators, and in fact, that's why Rational Rose kind of, I think, separated out the code generating feature from the interface and made it a different package that people could buy, because they didn't really want people using it for that, because it was a replacement for actually knowing what you're doing. So different types of program generators. I've mentioned already the Rational Rose kind of concept. In fact, this kind of spanned out of case tools, computer-aided software engineering. That's an archaic word that hasn't been used in years. But that was the theme of a lot of the pre-existing case tools. It was essentially an environment or a type of program generator that was an application that generated the code. So the application generator for, let's say, business data processing, parsers, lexical analyzers, code generators that were a part of the tools, of case tools in the old days. We actually still have in software development, so if you ever take a compiler design course, you can get open source Java parsers, Java lexical analysis, grammar, actually all of these toolkits are available to you, and you can generate code actually with them, so you can create your language and you can create all of the components you're going to use as input to specify the features of your language. And it actually does facilitate reuse, because you don't have to be a compiler designer to do that. You can actually just know enough to be dangerous, fill in the blanks with your definitions and make up your language, click a button, or compile the Java code, and all of a sudden you've written your own programming language. And then figure out how to assemble it. Figure out a little bit about assembly language, maybe. Add that in there. So generator-based reuse is cost-effective for applications. It's limited on a relatively small number of application domains. We don't have code generators for everything. We only have it for certain. In fact, right now, it's really just an object-oriented UML kind of generator, because that's really the easy way of doing it. So it's easier for end users to develop programs. So you don't have to be a professional. You can be an end user, and you can come up with some sophisticated design. See, this is why I waited till the second half, because we still have people coming in. All right, reuse through program generation. Well, that's a big X. There was an image, but it's missing from the slide set. I'm not quite sure what happened to it. It's probably not compatible with my Mac or something. But there was a case tool in that picture that showed you a little button. It said generate code. All right, component-based development. This is part of the architectural lecture that the architectural design lecture actually kind of left off at this concept. Mentioned it, but didn't go into the exact details. And this is an important concept actually for the final exam, because there are some questions, and I can just tell you right now, well, okay, small deviation because I'm thinking about it right now. For those of you who've sat through my Oracle information, and I told you it was a very hard exam, it was a very hard. This exam is extremely easy. So those of you who got tortured through Oracle can be rest assured and relieved that you're going to like this exam. And what I did actually, because we have so many different topics, I'm going to go through lecture by lecture. But the interesting thing is, for some strange reason, the reason why I'm mentioning it now, and the reason why I have to mention this, I have to go over this last lecture, heavy on components. Heavy on architectural design, heavy on the second part of the course for some reason. I don't know what happened. I try to make a unique exam each time. Sometimes, they end up being more difficult. Sometimes they end up being extremely easy. This one is heavy on architectural design and heavy on components and reuse and all this stuff, actually. Because this brings together a lot of the other concepts we talked about earlier in the course. So basically, that's how it turned out. So I know you're going to have some component-based development questions, because this leads into the architectural design of the system. And the components, if you're not familiar with it. In fact, the abbreviation component-based, CBSE, you don't really see that very much either. It's actually a not brand new, it's kind of old at this point, but it's a very common approach to development, where you've got, instead of objects or modules, now you get components, because the components can be of all different types. Now, originally it started out being objects, and turned into the blanket concept of component, which kind of leads me to believe, component might have multiple different definitions to it, and it does. So a component can be almost anything. It can be an algorithm written in assembly language. It can also be a GUI, a Java GUI front end written in Swing. It could be using, some abstract window toolkit and another object. It could use anything, essentially. It could be of different programming languages. So components could be the internet as a component. So developing software in this kind of fashion is pretty much the growing trend these days, because you get cross-platform compatibility, you get distributed systems. Nobody lives on an island on their own anymore. We have the internet around, we have networks going on. So it emerged through the failure of object-oriented development to support effective reuse. And single object classes are too detailed and specific. That's why I said don't confuse object orientation and that concept of reuse in components with component-based development. Component-based development is a totally different concept, but it's equally as important. It's what you're developing in these days. So components are more abstract in the object classes. They can be considered to be standalone service providers, which means you can actually outsource your components, and that gets into the service-oriented software. Software as a service. Cloud computing heavily uses component-based software. Because what have you got? You've got components that are out there that don't belong to the company that are part of your application. And as long as you have a constant connection, then, and that's the problem with cloud computing, you need that constant high-speed connection. If you don't have that, you're hosed. Your application's not going to run right anyway. But as long as you have that, who cares where the stuff is? Who cares who made that, who made this? And as a classic example of that, and some people are shaking their head going, I don't know what she's talking about. Every program that uses Google Maps, that is a component-based software development environment. You're using a component, you're using a service, a mapping service, an API that Google's providing to give your application mapping. If you're building an app for a Google phone or for an iPhone, you're using the services that are on that phone, the messaging service. You're not rewriting text messaging. You're not rewriting email capabilities. You're not even rewriting web development stuff. You already have the web browser built into it. You add the component to the interface, and your application is a blanket or a wrapper around all of these different components that are composing the application. So that's going back to my original comment. Yeah, 90% of all software is built as component-based software engineering these days, which is another reason why I couldn't leave this lecture out. But it's a nice one to leave with, actually. It's a nice concluding lecture, anyway. So, components provide services without regard to where the component is executing or its programming language or its interface. I probably described more than what was in the slide already. It's independent. It's executable code that is independent and can be made up of one or more executable objects, remote objects, local objects. Doesn't really matter where these objects are. Components may range in size from simple functions to the entire application system. And I would say Google Map applications are primarily mapping. They're heavy use on that component, actually. In fact, most of the application in the interface here, that's just a picture. In fact, that's a website that uses Google Maps, actually, but I don't know why the X is coming up, so anyway. So a majority of the application, or it could be a small portion of the application, and you can also mix components. So you can use mapping facilities with messaging facilities, with all sorts of different types of protocols and things, which is how we're building applications these days. So we have component interfaces. Very similar to object interfaces, and the difference is with this component environment is we've got provided, hopefully, so it provides an interface that defines the services and the components and how the components are supposed to be accessed and used, usually through an API, application programming interface. It's not normally something where they're going to give it to you. It's closed off. In some cases, if it's an open source component, it is given to you. A lot of the MySQL application development, it's open source. There's a lot of front ends. PHP admin is a great component. You can actually mix and you can actually pull code out of that, mix pieces of that. And if you're not familiar with it, it's an HTML interface to MySQL. Actually, works with any database. Nice utility, actually, provide you with for client-server interfaces with databases. But people have pulled out certain things and have actually included it in other types of web applications and utilities and things. It's open source, so you can do that. But most of these components are self-contained, executable modules. They come with an interface, come with a driver, come with an interface. It's like the old days. It's almost like we've gone back around to the days of the DLLs, the dynamic link libraries. Very similar with the shared objects. Very similar in concept in terms of old networking, old Unix days, where we'd borrow something and use something and call to something. But now we're looking at the internet. We're looking at global development. So, requires the interface. Otherwise, you can't get at the code. You need to know what the interface is all about. When you learn how to use the module, the component, you're learning the interface is what you're learning. You get information hidden from you because you don't know exactly how it's implemented. Rather, you're learning the interface. So that was a picture of something I don't even remember. Let's see. Component abstractions. Here's the vocabulary. We have functional abstraction, casual groupings, data abstractions. Most of you are familiar with functional abstractions and data abstractions if you're programming. If you're programming that. Cluster abstractions, system abstractions, just different levels and different vocabulary words to explain kind of the different levels of, it's the viewpoint. It's how you're viewing it, what label you're putting on the particular components. And I'm not rushing through, but I'm going to kind of go briefly through this lecture because I'm going to assume you guys are going to stop me, which nobody ever does if I go too fast. But you can also download it. It's lecture number 11. Look at. In terms of the processes, so we talked about software development life cycles, talked about how software is actually engineered. In fact, that was mostly software engineering 1, but we tapped upon it a little bit at the beginning of this course. We actually have component-based software engineering processes that differ a little bit. So we have the development that's integrated. So we integrate it. We look at reuse-driven development environments where we have platforms that are essentially designed to facilitate the reuse. And sometimes they're proprietary IDEs. Sometimes you're given, in fact, this goes back to the old days when you were given drivers and you were given stuff. And you had this little utility. You brought up the utility and you could set the parameters for the driver and you set all the information for the properties and everything, and then you included that in with your program, and then it knew how to communicate with the module. We actually have kind of a similar thing going on again in terms of the interfaces and the development. And the system requirements are modified to reflect the environment. So it's really just following, again, a modified software development lifecycle where we're either using a specialized IDE or a toolkit. We are modifying requirements to make certain that we've specified out different parameters and different settings needed for the package, the API that we're going to include. And we're making some special considerations, and we also might involve prototyping or incremental development processes, because what ends up happening with some of these reusable components is we don't really know what they're going to do. We don't really know what the effect is going to be. So we build a prototype, and because the module and the component is already built, all that work's done. Now we're just focusing on the user interface. We're focusing on the design of that reusable component. Can't talk today. We're putting it all together in a prototype that's going to demonstrate the functionality, hopefully. So, I don't know what that picture was. I don't know what that picture was either. All right. I gave you all the benefits, all the pros, to made it sound really, really good, maybe. And actually it is. That's what we're doing today. It's very powerful in terms of a methodology for building software. Here are some of the problems that are associated with it. The component incompatibilities may mean that cost and schedule savings are less than expected. Yeah, that happens a lot. Because here you've got a reusable component. Let's call it Google Maps. It's a service, actually. It's not really even a component. You don't even get it. You just call to it through the internet. And somebody actually has to invest some time to learn the interface. You can't just pick it up and use it. In fact, most people, they go, ooh, and then they find out what it's used. Oh, wow. And then the light bulb comes on. And then they're, oh, wow, I could put it in this application. I could put it in that application. Now I got overuse. Everybody's using it. Find my car in my parking space. Actually, the coolest thing I've ever had an app do was find an open parking space, which is kind of cool. but it wasn't very reliable. But anyway, different story. Someone's got to learn how to use it. Someone's got to learn. You have to invest time in it. It's not given to you. And sometimes you actually have to build fixes and wrappers for it. Sometimes you might, well, I want to build an application that doesn't go online, that's not online constantly, but it's going to use a mapping program. Okay, so you have to kind of build your own glue to glue your application to this service. So this application knows when to go online and get the data, and then you have to cache the service results, and you have to parse it and use it. It's kind of like connecting to a database that's not online all the time, or your application is not online. The database is too far away, unreliable connection. It might take you longer to figure out how to use it than just to write this functionality yourself. In the Google program, you wouldn't want to write that functionality because you don't have the technology, essentially. You don't have, unless you have your own satellites. You ever seen those little Google cars going around the streets? You see maps on them, navigating. They're actually recording like information from the streets and stuff. I don't see them very much in San Jose, but I've seen them like in Sunnyvale. Anyway, unless you have that equipment, you're not doing it. So finding and understanding the components, big issue. I would say probably the most important issue right there. Managing the evolution as requirements change and as situations where it is impossible to change the system components. It was built to work with a proprietary mapping program. And it can't be worked with Google Maps anymore. On services, this is another point that's not on the slide actually. Services are easy to integrate with, easy to use as components. Executable files, modules that are created, that are bundled with APIs that go along with them, they're constantly upgraded. And they also have bugs, and they also have problems. So you compile your program using this, and now we have an upgrade. So now you got to rebuild everything, and then we have we found a bug and we can't fix it because we don't own the source code. So you go back and forth with whoever wrote the algorithm, and say, hey, you had a bug. You got a bug. A lot of encoders are like this, actually, for people who write applications that do MP3 encoding, video encoding, which is actually kind of popular right now, or has been for the last several years. There's some seats up front. You find a bug, and then you have to work around the bug, which is kind of ridiculous if you think about it. And you can't fix the bug. And then you have people who actually try to fix the bug, and then they end up doing more work than if they just wrote it themselves. I think so. So evolution. Which brings us to the concept of application frameworks. Also another important concept that I actually covered briefly in the architectural model lecture that I needed to cover to fill in the pieces for what you're going to need for the final exam. The framework of the subsystems design made up of collection of abstract and concrete classes interfaces between the classes in terms of the objects, the components, the pieces of information, the data, the sources, external, internal sources of the information that you're going to be using. In terms of the application, so it's our subsystem of the application. And that's what you were doing with that mime pump. You were actually looking at the application framework, but you were also looking at the environment because you had something like water, I guess, or buckets, or maybe I should have read that description. I don't know. It's probably good that I didn't. Otherwise I'd give too much of it away. And as another side note, just in case I forget to tell you now that I got more people here, the due date for all of those assignments that I know you've done already, and you're just waiting, you're just dying to turn them in, because you finished everything for the course already, those are all due May 9th. So it's after. And for those of you who just came in late, I'm finishing up the last lecture, and then when this is done, I'm going to start the final exam review. And I'll show you the schedule one more time. But I thought, because I keep forgetting to say stuff, so I figured, well, I'm thinking about it, I'm just going to say it. May 9th is the deadline for all of those assignments. Some people thought it was the 24th for some reason. That's Easter, I think. Anyway, April 24th, that's Easter. You guys celebrate Easter, by the way? I don't know. I don't really celebrate Easter either. So. A lot of Americans do that. I was just curious. All right. So that was a nice tangent. All right. So application frameworks, subsystems. So the framework is moderately large entities that can be reused. So usually the framework is going to include the system, the middleware, or perhaps the enterprise application framework. So mostly we get the middleware is what we're interested in doing, bringing pieces together in terms of the framework. So we can actually model this, we can design this, we can put it together in terms of components. So our system infrastructure supports the development of the system itself, the communication, the user interfaces, the compilers, all the communication channels and things of that nature. Middleware integration frameworks are the standards, the classes, the support for the information interchange in terms of the middleware. And what ends up happening in most cases in terms of the framework classes, you have middleware classes to support the middleware that's already chosen for you. So if it's a .NET environment, if it's a JVM environment, you're actually looking at that in terms of the framework for the middleware, and you're building your application to work with that reusable component. Because, lucky for you, you don't have to invent .NET. I seriously wouldn't, but, although Microsoft did. I'm not a fan of the .NET, but, some people are. In fact, the world is full of .NET right now, and a lot of growth in that. And as an application framework, as a framework class, you would include that with your application framework. So your application framework works with the middleware framework that is in a category, and this is nothing more than vocabulary framework class, but what I'm going to do on the exam is hit you with the vocabulary, which is why I have to go over this lecture one more time, because you're going to want to know what a framework class is. What is a framework class in terms of the interface? And it's part of reusability, actually. The framework's given to you. You're writing an application that works on it. It's kind of like operating system support in the old days. But do we write applications for operating systems anymore? Nope. Everything that interfaces with a framework, because now we have cross-platform compatibility. Unless we're writing Microsoft Visual C++ or Microsoft anything. Microsoft is Microsoft. It's all platform specific. But the rest of the world, the Java route is not platform specific. We don't care if they have Windows or the Mac or whatever they are, Google phone or anything. It works on everything. So, all right, extending the framework. So if we don't like what we have, we can add to it, usually. We can also customize the framework as we can in the RMI environment, some of the other ones by setting security policies, privacy control, restrictions on the framework, parameters that are associated with it. So the frameworks are generic and are extended to create more specific applications or subsystems. This is where people create servlets in the Java environment, which are subsystem components. Actually, good point about Java. It's all component-based development, component-based software engineering, actually. You have a servlet environment if you're doing that, and you have beans. You have a Java bean for this, a Java bean for that. Those are components, and you're doing component-based software engineering when you're designing an application that works in that environment. You have the framework of the middleware, the JVM, the RMI, the JDBC, whatever it is you happen to use technology-wise. Then you have your components, and when you need something, you just call a reusable component out of the repository, and you say, here, give me one of these objects. Okay. And you makes a copy of the object, makes an instance of the object, puts it in a manager that keeps track of it, and you just call it that single object. That's reuse. That's reuse to its maximum, actually. Because now you have runtime reuse as well, rather than having multiple instances of a particular object running in a regular environment, which is why people like the entire Java networking, the Enterprise Edition, because it's definitely efficient. There's definitely a wave, and a lot of people are using it these days. So, all right. So extending the framework involves adding concrete classes to it. You can actually extend it by adding your own classes. It's user-defined classes, inheriting operations from abstract classes. We actually saw this. We extended the framework for the collections API or package in the object-oriented design class. If you're taking that class. We built upon a list, created array lists, linked lists, kind of extended that functionality in a lot of different ways. You can add methods that are called in response to events that are recognized, hopefully, by the framework. In fact, a lot of the frameworks themselves these days are meant to be inherited from. They're based, some of them are even abstract classes. They're meant to give you the foundation for the functionality for which you're going to grow your application from. You're going to create your own functionality. Problems with the framework, it's either complexity and time it takes to use them efficiently and to learn about them, And then sometimes, not in the Java world, but sometimes when one component fails, or one of the pieces of the framework doesn't work properly, the whole thing is hosed, which could be kind of drastic. So, some of you may or may not have heard about the Model View Controller, which is also an architectural/reuse feature. It's an environment. So it's a system infrastructure framework for GUI development. Usually when you take an object-oriented development course, if you took Smalltalk, if you took an older class, if you take a programming class, maybe C++, sometimes they talk about the Model View Controller. There's some seats up front if you want to sit up here. You don't have to bring in your own. It's a bring your own chair day. See that? Wait till everybody arrives before I start talking about that final exam. Smart. It's getting there too. Probably within about 10 or 15 minutes I'm going to switch into it. But all right, so the Model View Controller allows for multiple presentations of an object and separated interactions with its presentations. So you have a repository of objects, and you use the Model View Controller to not only design the interface to those objects, but control the activities that are going on between them. So you're really looking at the identities, the states, the behaviors, the interaction, and it's a great object-oriented type of toolkit, but it doesn't really give you the object-oriented design. It's not a full-featured kind of system, and it's more of a methodology versus a system. It's the IDE that's going to build in the concepts into the way that the application or the IDE is actually working. So the Model View Control Framework involves the instantiation of a number of patterns. And we're not going to get to the patterns, to the design patterns. All right, so I talked about COTS already, so I'm going to kind of skip through that. This is where I start skipping through because I kind of overtalked in the beginning anyway. So we already looked at COTS system integration problems with interoperability, lack of control. We all know what COTS are, hopefully. Commercial off-the-shelf systems. A word you want to be familiar with for the final, actually, because I use vocabulary. Oh, that's interesting. I think that computer just did something. Maybe it's instant messaging me or something. All right. Component development. Let's see. Component reusability, trade-offs between reusability and usability. Actually, that's kind of an interesting point there. In fact, that's what happens with security usually sometimes when it's implemented. We have a situation in which, the usability is suffered from the reusability because we've reused so many different components that the user's got to go through 5 different screens to get to something. Or a piece of data has to be converted to this, to this, to this, and it takes too long. And then sometimes it affects the usability of the system, sometimes not. Or maybe the features that the system has, because we're using this module, it only prints to HP printers or something. Or, it affects the usability somehow. So let's see. Reusability components themselves, actually kind of went through this already in terms of some general characteristics about them. Usually the development cost of the component is higher than the cost of the specific equivalents if we were to develop it. Extra reusability enhancement costs should have an organization rather than a project cost. So it's usually not per project, because if you do your pricing model so that it's based upon what it costs you to build the program and you're intending to reuse the program, you're reusing components of the program, it really makes the program look not profitable in the end because you've spent so much time and energy, but you've reused that component over and over again, hopefully. So you actually have to balance out the costs if you're playing that route for that game. So generic components may be less space efficient as well. Actually, that's a good point because every time we have reusable components in any type of environment, there's extra support for everything. Because not everybody's going to use the same component in the same environment. So you have support for this printer, that printer, that printer. You have a bunch of extra information in there because it's generic in nature. And it's not specifically designed for your application or your purpose. So, in terms of reusability enhancements, name generalizations, operation generalizations, exception, component level certifications, all kind of different terms of enhancements. Names of the components might be modified so that they're not directly reflecting upon specific application entities. So you have some customization that can happen in terms of some of the different enhancements that you can add to the components. You usually This list is kind of deceiving because it really depends on what component you're working with as to what the vendor is going to give you. Sometimes you can actually, they give you facilities or they give you tools to actually come out and enhance, modify, add your own logo or something. It's kind of like when you use, like, let's say, like Moodle or something, or some of the web development environments out there where you can take out the company name, like put in a logo or something. Those would be considered enhancements that you're using a reusable component. Actually, it's a whole software package you're reusing, but you're able to customize it. This brings us to the concept of application families. This is not inheritance, although it sounds like it. So we have families of applications, where we have application families or product lines that are related to sets of applications that have common domain-specific architectures. I mentioned one already, the .NET applications. That's a .NET Microsoft family. We have the RMI family. We have Java, generic Java family of applications. And what's happening today is because, engineering of these software applications is so different depending upon the application family that we actually have to follow different methodologies. Sometimes, different model view controller would apply towards something, would not apply towards something else. You do .NET development different than you would do a Java application development, things of that nature. So, common core of the application family is reused. Each time the new application is required, and each specific application is specialized in some way. It's like why people use .NET, actually. It's because all of your networking stuff, all of those tools are built into the framework. So every application uses the same protocols. If it's going to bring up a web browser, it's going to bring up Internet Explorer, but it's going to bring up everything the same consistent way. What do you get with that? Reusability. What else do you get with that? Reliability, dependability, ease of installation, and ease of creation. It's efficient, hopefully. It's optimized. So then we have specializations, platform specializations. .NET would actually be a platform specialization or a middleware specialization. We have configuration specializations. That would be more of a networking protocol, something to work on a distributed system versus a client-server model or peer-to-peer model, something of that nature. And functional specializations in terms of creating customers with different requirements, with different function sets. You get the functional specifications with different operating systems that, actually, we get that with Microsoft. With Windows, actually. We have, what was it called, the professional version, we have the business version, and we have the home version. And so technically the function of that system is designed towards those three different categories. Outside of the lack of support for some things, that's the only difference I see, really. I don't think the home version runs any faster or slower. Actually, I think the professional version runs faster, for some reason. But all right, inventory management systems in terms of reusable components. We have resource databases, where a good example of that would be servlets. We have a directory where we put all the resources, all of the Java beans and things that we want to use in our server. So, and we bring them up out of the same location, and it has a general scope in terms of the servlet when it's read and open. I/O descriptions, query level access interfaces are all some examples of that. So. In terms of the application, and we are getting towards the end of this, application family architectures must be structured in a way that separates different subsystems and allows them to be modified. So, the .NET actually is a good example of that because there's wizards, there's application generation tools within the .NET Studio that, I want to create a web application, so it gives you ASP, and it gives you, all of the different things you might need. That's application specific, that's in the particular architecture. And it leaves out everything you don't need, essentially. So it should be separate entities described in details, hopefully. Library systems themselves is another example. And these are different architectural systems that facilitate reuse. In a library system, we all use those before. We have books that we look up. We have card cataloging. So we get cataloging, tagging, things of that nature. Library system, repository systems are just architectural descriptions of different types of utilities or different types of tool sets that we run into in terms of being able to reuse certain concepts. Family member development, I can skip that. Design patterns, I could skip that too. Don't really need that. Observer patterns. We don't need to know anything about design patterns for the final exam. For those of you who came in late, this is lecture number 11, and it is the last lecture of the particular course. But we need this stuff for the final exam, so I had to cover it. We're getting into the final exam review next. All right, so let me give you some summary key points to remember out of this particular lecture. We design with reuse. It involves designing software around hopefully good designs and existing components. It's not software reuse in terms of object-oriented design, although that does facilitate reuse. We're talking about component-level reuse. Advantages are lower cost, faster software development, and lower risks, hopefully. Component-based software engineering relies on black box components with defined requirements, hopefully. So we have black box. We don't have any white box components. So which means we're just using functionality that already exists. And what does that say? Off-the-shelf software product reuse is concerned with reuse of large off-the-shelf systems. Accounting systems are actually very popular for that, and then they get modified. Okay, software components for reuse should be independent. They should reflect stable domain abstractions and should provide access to states through their interface operations, hopefully. Application families are related application developments around common cores or common areas like .NET and JVM. And this is actually, the key points in this lecture is actually good in terms of a summary. That thing made another noise. So many distractions today. And design patterns are high-level abstractions that document successful design solutions. So, right, that is the very last lecture. Don't leave. You guys don't. I don't even know who's even getting up. That's good. The next part is the final exam review. I'm going to stop my recording and start it again.